Hello and welcome to my channel. This is a simple hinge joint. If you take two parts like this with a cylindrical shape, you can make the rolling joint, which moves like this. To make this joint you can use kind of string which you can put like this and like this, or you can use the cables or ribbons, and like this you can make this joint even without any bearing. There are also another way how to make the rolling joint. And here is the example. So this part is one of the part of the robot arm, this one is another part, and there is two parts like this which are fixed over here and over here. And so it moves like this. And actually this is also a rolling joint, and in order to prove it, let me fix this circular shape piece and this one like this symmetrically. Yes, seems fine. And now when I rotate it, as you can see, one rolls on another. But I would like to make this in 2D. So this is a 1 degree of freedom joint. I would like to have the 2 degrees of freedom joint. And instead of two parts like this, we have three parts. And so it moves like this, also like this, and actually it can rotate. So it's 2 degrees of freedom. 1 degree of freedom, 2nd degree of freedom. Usually this is called virtual sphere rolling joint because it moves like two spheres rolling one on another. But from mathematical point of view, these are not really spheres. So this is just an approximation of the rolling sphere joint. So I would like to use 3 stages like this to make 6 degrees of freedom robot arm. Huge thank you to Robotics for sponsoring this video, more about them later. This is already the third prototype, and this third prototype, it can rotate almost 90 degrees. So 90 degrees in this direction and 90 degrees in this direction. Almost 90 degrees, not exactly, a little bit less. I also have an old video of the first prototype, and for the second prototype I have not made a video because I quite quickly realized that the second prototype was not good enough. So this is the first prototype, and here I have the really short distance between this axis and this axis. I quickly realized this, and so in the second prototype I increased this distance, and afterwards I realized that this form of the leg is not really optimum. Maybe it's better to call it link, not the leg. This form of the leg or link is not really optimum, and that's why I changed it over here and I made it like this. And this is the current prototype which you saw. Actually, I looked a lot at this kind of joint from a mathematical point of view. And I even did my own calculations, somewhere here, where first of all I figured it out that this is not exactly a rolling sphere joint, and afterwards I thought that it's not going to work, and after I decided yes, it's going to work. And it's going to work because I have only 3 legs. And you can think that you can make this kind of joint with more than 3 legs, but from mathematical point of view you can make this with more than 3 legs only if it's going to be the perfect rolling sphere joint. But this is not perfect rolling sphere joint, it's approximation. That's why with the 4 legs it's not going to work. That's why I made the 3 legs. With 3 legs it's going to work. It's working, it's not going to work, it's already working like this. Now we need to motorize it. And this one is a little bit heavy and big. I would like to make it small because I would like to use the cheap servos, the cheap parts. Like this you can repeat this project if you want. It is difficult to model this joint in the CAD, and because of this what I did, I actually made it in the CAD, but I have not tested for the self-collision in the CAD. Afterwards I 3D printed and I tested for the self-collision like in reality on the 3D printed model. But because of this, it's a kind of complicated project and it takes a lot of time. For example, like here, I figured it out that this part should be quite far from the center. It should not be like this straight, because otherwise it would collide this part with this part. But if it's too far, now it's a little bit too far. In this case, it will collide over here. I use the bearings here everywhere, and that's why the motion is really fluid. This robot arm is going to be kind of test robot arm, so I don't want to make it expensive. And that's why this particular joint is not very suitable. I mean, this design is not very suitable because it's quite bulky, it's big and it's heavy. And I would like to use quite inexpensive servos in order to drive this robot. This servos needs to be quite precise, and that's why I choose the DYNAMIXEL servos. over here. And huge thank you to Robotics company for sponsoring these servos. I'm going to use 3 quite powerful servos in the base. This is the name of the servo. It costs $50 per servo, around $50 per servo. And I'm going to use 6 quite cheap servos. This is less powerful. This is $22 per servo. So in total it's going to be 9 servos for the 6 degrees of freedom. And all this I'm going to control with the new OpenRB-150 board. And this is a super new board, and that's why it's written here by hand, OpenRB-150, because this is a pre-production unit, but it's working unit, so we're going to use it. Huge thank you to Robotics company for sponsoring the hardware for this project. So this is a big servo for the base. And this is the smallest servo which we're going to use. And this is OpenRB-150 module. It has a USB-C, possibility for the external power supply. You can also solder here the XT60 connector. And you program this board simply with the Arduino. And what is important is that this is not just a shield, this is a real board with microcontroller on it. So in order to run your DYNAMIXEL servo, you need only this power supply and nothing else. So in order to use these servos, I need to make this smaller, shorter, and also lighter. And this is what I have designed. So this is a base for this robot arm. I only put here 1 link, but it should be 3 of them. You just need to imagine them. And over here there is a DYNAMIXEL servo. So this servo drives this red gear, and this red gear drives this part. And there is a reduction ratio 1:2 between this gear and this one. And also this red gear is supported with additional bearing over here on this green part. After on this base we're going to put this second part with the smaller servos over here, but basically it's the same but smaller. And after on top of this we're going to install the third part, even smaller than the second part. And on this third part I have not put any support for the gear, because I suppose here the forces should not be very high, so it should be good enough like this. And I have already started the assembly. Let me show you. And so this is a base joint. You see it's way smaller than the original one, and also it's way weaker, so I don't use the bulky parts, I use the smaller part and the lighter parts. And it's going to be driven with these 3 gears. So actually with these 3 gears we would be able to move it everywhere. And this one is not really good, because it cannot really get to the 90 degrees range everywhere, because over here it's a little bit smaller, or maybe it's 90 degrees. Yeah, it's 90 degrees, but still I improve it, because right now there is a collision between this gear, you see this gear over here, and this link. And so this is the next proper iteration. Here there is no collision. And it seems like it works perfectly. So this is a joint of the base. This smaller one going to be the joint in the middle. And this small one is going to be the joint at the top. So this basically is going to be output. He is the smallest and the cutest. And just to prove you that it was not easy to design, here are the failed links. Maybe it's not so many, but still it took some time. And this is a base with the 3 servos installed. There is a gear at each servo, and there is a bearing which supports this gear. All the servos are daisy chain connected, and this is the output. This is a servo with ID 1, 2 and 3. So I changed the ID of the servos beforehand. After over here this piece, and after this piece the joint itself. The test of the initial Arduino program went well, so I continued with assembly. Cool! And this is how OpenRB-150 looks like with this XT60 connector. So the base, the middle module, and the top module which goes on top of the middle. They're all connected together, and let's see if this OpenRB controller can control all 9 motors at the same time. This is the first time that I'm trying to run it. The power, the power for the controller. This is cool. It worked. Yeah, with a lot of vibrations, but it worked. To power up this robot arm, I'm going to use this battery. This is a LiPo 3S, 3 cells. And I charge this battery to the 12 volts, so 4 volts per cell, because the servos at the base of this robot, they support 12 volts, not more than 12 volts. For the first test, I decided to run it under the table. Like this, if the servos are not powerful enough, the robot would not be able to reach desired position, but at the same time, it would not overstress servos. So it's safer for servos like this. And so it was working okay-ish under the table, but I would like to run it when it's standing on the table. But when it's standing on the table, it's not powerful enough. So in order to do something with this, I used the carbon fiber rod. So actually I use this rod in the base link, and this means that over here inside I put this rod, which is connecting this part and this part. So this rod is going to help to support the robot arm. So it's going to help to the servos at the base. But the problem is that such kind of trick I can use only in the base link, because only the base link is standing upright and the other links, they are moving. This means that if I put also this kind of rod over here, for example, in the second link, in some cases it's going to help to our servos, but in other cases it's going to make the things worse. So that's why it makes sense only to make it over here in the base. But I have another possibility how I can make this link and this link a little bit more powerful. Right now the base servos, they are running at 12 volts, and this is the maximum voltage for these servos. But the servos at the second link and the servos at the third link, they are running at 5 volts, and this is also recommended voltage, but I can go to the maximum voltage, which is 6 volts. So probably I will try to run these servos at 6 volts like this. Probably I will have a little bit more power. And I hope that I'm not going to fry these servos. So right now let's try with the 5 volts, and I'm pretty sure 5 volts is not going to be enough. It does not easily keep itself upright. Oof. It's really struggling. It should be 90 degree, but it's more than 90 degree. Now the same test, but at the 6 volts at the second link and the third link. It's still heavily underpowered. Like heavily. I have decided to disassemble the top part. So like this, instead of 6 degrees of freedom, it's going to be only 4 degrees of freedom and only 2 links. But at least like this, I hope that it's going to work properly and the motors, the servos are going to be powerful enough. Also, I took out this carbon fiber rod. So let's run it like this, and maybe in the future I will make another link which will go over here, so instead of base. So this is going to be like extremity of this robot arm. And this base should be really powerful, and like this we will have the 6 degrees of freedom. But for the moment it's going to stay 4 degrees of freedom. And this is going to stay like this. It's actually quite cute. It's small and cute. If you really would like to see this robot arm in 6 degrees of freedom configuration with the 3 links and not only with the 2, put the like to this video. Also promote this video. Like this, robotics company will see that this is something interesting for the viewers, and they will provide me 3 powerful servos, which I need for the base. So it's up to you. As you can see, it has quite significant play, and most of this play comes from the backlash in the gears over here. But what we can do, we can pre-tension the servos. So we're going to move a little bit the servos in the same direction, like this. They're going to pre-tension all these gears and reduce the backlash. And this we can do because we have this special configuration with the 3 servos which can control only 2 degrees of freedom. So now the play is like this. And you see now the servos are pre-tensioned. Actually the play is huge, but now it comes only from the flexing of these legs, of these parts. And it's not coming from the backlash of the gears. Now the gears are pre-tensioned and they don't move anymore. Cool, this is a nice feature of this configuration. So finally we made the robot arm with the 4 degrees of freedom, not the 6 degrees of freedom as we planned in the beginning. But still it's enough in order to make the conclusions about this mechanism, about this idea. I have made the list of the 4 advantages and 3 disadvantages. So let's start with the advantages. First of all, there is possibility to compensate for the backlash. And the second, this kind of parallel mechanism. So each of these links is a parallel mechanism with the 3 servos which controls 2 degrees of freedom, meaning that these servos, they are working kind of together. The third advantage that in this kind of system, this kind of joint, there is a place in the center for the wires. So the wire management is quite straightforward and easy, like it's here. The wire just in the middle, and it's perfect. The fourth advantage is that the motion of this robot arm are quite cool and unique. Now let's talk about disadvantages. First of all, the volume for the servo motors are really small, because a lot of volume are taken by this mechanism, by these links, by these legs, and that's why the volume for the servo motors is only here, and so you cannot use a big actuators in such design. The second point, there is a bad mechanical advantage in this joint, meaning that if I move the joint 90 degrees, like here, this part moves only 45 degrees. And that's why I used the gears over here with the mechanical advantage of 2, and thus there is no mechanical advantage between the servo motor and the output. Meaning that if the output moves 90 degrees, the servo motor moves 90 degrees too. And the third disadvantage, there are a lot of bearings in this system, and that's why it's kind of complicated. Thank you for watching this video till the end. Huge thank you to people who support me via YouTube channel membership and via Patreon. Here are their names. Thank you guys and girls, you are the best. I really appreciate your help. As usual, stay safe, good luck with your projects, and see you next time.